So this is another type of core loss of transformer called hysteresis loss. What is hysteresis loss? Hysteresis loss is nothing but suppose consider a ferromagnetic material. Suppose this is a ferromagnetic material, right? This is a ferromagnetic material and it contains lots of tiny magnets, right? And if it is wound by a current conducting coil and voltage is applied across it, what will be for, and if a AC current flows through it, these tiny magnets aligned north pole south pole for a particular, this magnets is aligned to the north pole and south pole of the material, and for negative cycle, say for positive cycle, this will be north pole south, and for negative cycle, this tiny magnets just aligned north pole south, like this. First it is like north pole south pole, and for negative cycle this will be north pole south pole, and for every cycle this phenomenon can be observed. Due to this, heat is generated across the material, and this heat loss is called hysteresis loss. Okay, now suppose if I draw, suppose this is current and this is your time axis. So this is the sinusoidal path of the current, and this is pi by 2, this is 0, this is pi, this is 3 pi by 2, this is 2 pi. Right. Now and this is your magnetic intensity, and this is flux density B. Right. Now if current when the current is increasing through the material, this BH curve will also rise, but at certain instant this will be proportional, but after a value of current, the intensity will not increase and it gets saturated like this. And when the current is decreasing to 0, it will flow back, but it will not maintain the same path. There is a small amount of magnetism left in the ferromagnetic material. This is called residual magnetism. This is called residual magnetism. Okay. Now, if further the current is flowing in the negative direction, the plot will be like this, and this is called retentivity. This negative field intensity is called retentivity. Okay, and when the current will rise again in the positive direction, this completes the path. So this loop is called hysteresis loop, right? Okay, let me erase this thing for better visualization. Okay, let name it 0, A, B, C, D, E, F. Okay. Now, and this is your B max, right? This is your B max. It should not write B here. A, C, D, E, F, G. Okay. Now can see that for this is not T, this is omega T. For 0 to pi by 2, if we draw the coil, and this is your induced EMF E and current flowing through this, right? Now current is in the direction of the positive sign of induced EMF, then it can be considered as energy absorbed. Okay, energy absorbed. Energy absorbed, what will be the area of this? Means what is the magnitude of the energy absorbed? It will be, suppose H. Energy absorbed is O A H O. Area of O H A O. Right. And for omega. Hey friends, I am just taking 20 seconds of your valuable time. I hope you have subscribed my channel. If you are not, then please subscribe it, because this contribution from your side will really encourage me to do more videos like this. And if you find this video helpful, then please hit the like button. Thank you. Say pi by 2 to pi by 2 to pi means pi by 2 to pi. Suppose this is E and this is the direction of I. No. This is the take the direction of I is this, and the induced EMF will be this, and current is injecting the negative polarity of induced EMF. Then it can be considered as energy returned to the source. So energy return to the source. So what will be the magnitude of energy return to the source? This will be area of CAHC. Okay. So this is the whole area, and area where energy is absorbed, and this is the area where energy returned to the source. So ultimately power loss will be this area, means total area is this, and energy back to the source is this, so ultimately energy loss will be this area. So means energy loss we can write as energy loss is area of this total OAHCO minus area of CaHC, right? This is the energy loss of this path. Now what will be the hysteresis loss? Hysteresis loss is total energy means total area of this hysteresis loop in one cycle. For one cycle, total area, this is the total area of the hysteresis loop. So hysteresis loss total area of the hysteresis right. So what we can observe that if the area of this hysteresis loop is narrow, then there will be less hysteresis loss. And empirical formula of P hysteresis is, if I can write as P proportional to B to the power 1.6 into F. This 1.6 is the Boltzmann constant. Okay, and this is not B max. This is B max, and this is also proportional to F. And you can recall the eddy current loss P proportional to B square F square. And these two results are very important. Many problems come from these equations. Okay, now what we can get from the analysis, that if area enclosed by the hysteresis loop is reduced, means narrow hysteresis loop, area enclosed by the loop decrease, then hysteresis loss will decrease. And from that formula, if B max, like eddy current loss, B max decrease, then hysteresis loss will decrease. And third is obviously frequency, but we cannot take the frequency because this is a system frequency, right? And how B max can be reduced? If we use a material where B max is less, say for example CRGO, cold rolled grain oriented iron. This material can be used for building the core material for the core, and these have less Bmax. Okay, so ultimately our total core loss equals to PAD plus P hysteresis, and this is equals to, say, take a constant Ke for eddy current loss, and this is B max square F square, and take constant AH for hysteresis loss, and this is equal to B max 1.6 into F. This expression is very important from problem and gate examination point of view. Okay.